Okay, good. There we go. So, or not. Right, I'm going to run through very, very quickly. I'm going to try and give you a sort of broad overview of how we do dolomite hazard investigations using gravity. I'm going to start with a little bit of history, then outline the typical process that we follow, talk a little bit about where I think we go wrong, and then perhaps a little bit more about the relationship between engineering geology, hazard investigations, and geophysics. The sinkholes really hit the headlines in the 1960s, and this big one here was December 1962, where a crusher plant took, I think it was a total of 32 people down a sinkhole. Interestingly enough, they were spread demographically correctly. So the correct percentage of people were white, correct percentage were black, and of other colors. So sinkholes do not discriminate. I just thought I'd get that in there for those of you who might want to ask the question. But of course, the one in 1964 is the one that really hit the headlines, and for some reason, it's the one that's remembered more. A family of five died in that sinkhole. Their house was swallowed up in the middle of the night. In any case, all of that drove a massive investigation into how do we find where these sinkholes are going to happen. And I was looking through the Kluivert and Ensslin paper. We suspect a forefather, or either that, or if you have the name Ensslin, you're doomed to become a geophysicist. But Kluivert and Ensslin in 1973 addressed the International Association of Engineering Geologists, I think it was in Germany. And this comes out of their abstract, and I'll just read it very quickly. Despite intensive efforts by numerous organizations to develop a geophysical technique to locate subsurface voids which could possibly collapse to form sinkholes, no method proved successful. And the committee, I'll explain their name just now, had to resort to a method of evaluation of relative safety by considering chiefly the nature of the overburden, the configuration of the subsurface dolomitic bedrock interface in relation to the depth of the original water table, I'll talk more about that just now, and the water level drawdown. Information on the subsurface bedrock configuration was obtained from gravity surveys, while the other parameters were obtained from boreholes sited chiefly on the basis of the gravity data. Now, not much has changed. The CTC, I abbreviated it. It should stand for the State Coordinating Technical Committee on Sinkholes and Subsidences in the Far West Rand. It took an entire paragraph on its own. It was a very effective committee, though, and did a lot of work. So let's go and talk a little bit about why is it so difficult to predict where a sinkhole is going to develop. We, first of all, deal with highly variable overburden in the dolomitic areas, anything ranging from Karoo supergroup shales, mudstones, sometimes coal deposits, and sandstones, all the way through to the dolomitic residuum, which in itself varies dramatically from very low density soils, the famous WAD, if you're familiar with it, the manganese-rich soil, which has densities of 1,000 or even less, sometimes 900 kilograms per cubic meter, a dry density that is, and then that ranges through to the chert gravels closer to the surface, and then sometimes quite thick red aeolian soils, Kalahari sands that have been deposited as well. So that's the first problem that we deal with. The second is this multi-layered cave system that often forms in the Dolomites. If you've been into any of the cave systems or read any of the papers by Jacques Martini, Margaret Marker, the geomorphologists who studied these things back in the day, you'll understand that cave systems are not only extensive, often extending for many, many kilometers, but they are usually at several layers as well, depending on where the water table was historically. So that's a complicating factor. And then, of course, there are multiple conduits that might access the cave systems below. So that adds another dynamic to trying to predict where the sinkholes are going to develop. Last but not least, the water table. That, as I mentioned earlier, was very important on the Far West Rand because it was the drawdown of the water table that triggered the sinkhole development. A number of other sinkholes did develop post the drawdown, which were more related to infiltration of water from surface. And these days, SANS 1936 requires us to do two scenario assessments with respect to hazard. One is with respect to what happens if water runs in from the surface, runs down from the surface, infiltrates the substrata. Will that trigger a sinkhole? And then the second scenario that we examine is what happens when the water table gets drawn down. Because in itself, the movement of the water table might trigger a sinkhole. So the water table position and whether it's going to be dropped down is in fact a really important facet. So very important for us. Right, so just to summarize then, hazard assessments are a function of bedrock morphology, nature of the overburden, and the position of the water table. The water table, I might just add while we're talking about it, is quite crucial for us in the ingress scenario, because if it's above the bedrock, it means that any water percolating downwards, as soon as it hits the water table, it loses its energy. Okay, so it has kinetic energy as it's moving down, hits the water table, it loses that energy and the ability to then erode soil into a cavity lower down. So the water table can be a massive stabilizing factor. Drawing it down can be a real problem as a result. Now, what we find is that one geophysical test method for the ground might pick up one of those three things, but it's very rare that it'll pick up all three of them successfully. So quite often, ideally, we really want to be able to apply more than one geophysical investigation on the surface to help us identify these things and more precisely locate them. But time and cost constraints, and believe you me, the clients put a lot of emphasis on cost these days. It tended to mean that we use the most useful of the geophysical investigative techniques, which has proved to be gravity for the most part. Right, so how do we define hazard zones? Well, if you were to imagine that this was a section through a gravity survey, that would be an anomaly that is high, that would be a gradient, and that would be a gravity low. Possibly these two would be regarded as plateaus as well if they were flat enough and extensive enough. So we would then identify that as a bedrock morphological zone, that one is another one, and that one is a third one. I doubt very much, unless you're doing really intensive gravity, closely spaced station investigations, would you pick up this kind of detail over here. We have certainly tried doing that in shallow dolomite areas with some success where we've used a 10-meter spacing. But the client in that particular case did it just once and said, I will never spend that amount of money again. I don't see the value. So we define the bedrock morphological units, and then we go on and examine the nature of the overburden. So that's where the drilling in particular comes in, the ground truthing. How deep are these units? How variable? and then what is it that lies on top of them. And then, of course, the water table. If the water table is not found in those boreholes, we quite often want to know where, if it's a dewatered area, where the original water level was. So you'll quite often see people refer to the OWL. What is the original water level? And historically, I mean, Waterfez's records maybe stopped a few years ago, but we can go back and see how much what level it was at, because it has quite often been affected a lot. Okay, so the gradient is very important to us because that quite often is where these cave systems come to light. That's where they start extending out through the bedrock. So the gradient is quite often, both Clavert and Insolent talked about it. Many of us who work in this arena find that the gradient is where the sinkholes quite often happen. It's not to say that they won't happen elsewhere, but that is what it is. So we do a gravity survey on a 30-meter grid, typically drill the anomalies. We get a report from the geophysicist quite often, even though we do the drilling and give them the results, the residual gravity map doesn't change much from before the drilling. And we then go and analyze the boreholes and define the hazard zones. So this would be a typical drawing where we've done the gravity survey, we've done the drilling, we have our residual map, we go in and we analyze it and we zone it accordingly, each of those colors or zones. So the boreholes are analyzed and we then use the gravity. Where does it go wrong? Okay, two things. One, we join the dots and we stop talking to the geophysicist. All right. So just a quick one. This is a typical join the dots, or rather, this is an isolate the dots. So people attempt to take out the bad boreholes from all the good ones, and they say, that's a bad zone, that's a bad zone. Yeah, there were three, even though that whole unit might be the same thing, those three are bad, we're going to join them together. So they join the dots. This is another example of what happens, and quite often this is because people do the gravity survey, they drill 5 or 6 boreholes, they find they don't fully understand it, they go back and drill a few more boreholes, and then they give up on the gravity survey. They literally turf it out the window and they stop using it. And so the zone boundaries, now these are the gravity contours underneath, sorry, the zone boundaries now start crossing what we would have regarded as a morphological unit, a hazard unit. So ideally, this should be an iterative process, okay? And we have done that on several occasions with great success. This is a recent one that Geophys has been working on with us, where the left-hand one is the original survey from 2002. Hundreds of boreholes have been drilled, well, not hundreds, but scores. And I got him to rework this and we come up with something quite different. And the initial, I haven't finished doing the analysis here, but we have already some prominent features running through there which appear to be dikes, which weren't picked up before and which weren't obvious. So that iterative process needs to happen with you geophysicists. We can't ignore that, I believe. I would suggest to you guys, before you provide us with a quote, geophysicists, get some details. Find out what is the development, TSF, multi-story development, township, new mine. Quite often we will tell you, but maybe we don't. Make sure you understand what is the expected geology, and then depth to bedrock. Do we have some idea of what it is? Where is the water table? And then suggest additional or alternative methods that might be applicable, and then please get feedback from us. Insist on it, okay? Talk to us, and we'll try and talk back to you. All right, I've run out of time. That's just a story which I love telling because it disses engineers, but No, it's called Weber's Folly because Harold Weber was my boss at the time. A wonderful man, very genuine, never scared to tell a story that is self-effacing. walked into my office when I was a junior. I was working for him. And he said, "Oh, that's Weber's Folly. This is the cover of Tony Brink's Volume 1. And I said, "What do you mean?" And he said, "Well, I had that job. I was given that job. It's for a radio mast. The case study is actually in there, although Harold's name is not mentioned." And he was given the job to give a foundation solution. He went in, drilled 3 holes. He knew it was dolomite. And he came up with, of course, radically different results. Bedrock at 1 meter, bedrock at 16, bedrock at 10 over there. So he went back to the client and said, "I need a bit more money. I need to drill more holes." They gave him a bit more money. He drilled another 3 holes, came back with even worse results, just as confused. He went back, as he said, cap in hand to the client, and the client fired him and appointed Tony Brink, who then, in those days, rands and cents weren't around. Harold said he paid each of these guys £1 and gave them spades. They excavated these trenches, exposed the pinnacles. Tony Brink mapped them and he gave them the foundation solutions, just span from pinnacle to pinnacle with ground beams and put your tower on top. So it illustrates for me the value of engineering geologists and geophysicists. I've included you guys this time because I think a detailed gravity survey would probably have picked that up as well. But the value of understanding cost, which I think Harold didn't at that stage, and then the value of selecting the right investigation technique. All right, thank you very much.
Thanks, Tony. Are there any quick questions for Tony?
So on one of your slides, you mentioned that when we are mapping the gravity survey, we need to do the iterative, processing. What do you mean by that? Are you meaning that we need to do more data points?
We need to remodel. Yeah. So instead of just having 4 boreholes available, you've now got maybe 15 or 20. That's going to shift your bedrock pattern. And you can remodel, I suspect, as DP did. He could probably explain wherever he is the technique that he used in this particular instance. But that is what we ask for. I have done the same in the past with that very first gravity survey that I showed, where again, initially it made no sense to me. The borehole data was coming back and I couldn't differentiate between one side of the site and the other, but there was clearly 2 different zones. And I went back to Richard Day, I think it was in those days, and he reran the model. In fact, we had 3 reruns, and he came back with the 3rd one, which then actually predicted the zone boundaries much, much better and gave us a very clear definition. Yeah, it was very useful.
Second question. So we know that boreholes, they usually give us like vertical information. At what stage do we map the borehole if we want to know the extent of the size? Like at what stage when we have to sync maybe the camera to map the cavities?
We very rarely find cavities in boreholes. Very, very rarely. We tend to get zones of air and sample loss. Occasionally, the drillers will tell us that they've intersected a cavity, but it's very, very rare indeed. And quite often when we've examined those boreholes with cameras, for example, we find that they're not actually genuine cavities, but rather zones that have been hollowed out by the drilling process. And one of the really big problems that we currently face in the industry is that the drilling techniques have become so powerful and so quick that quite often the guys are drilling so rapidly that they lose air and sample. They're not taking the time to flush the material out. And so we're getting a kind of falsely high hazard being logged instead of what in the past with a less powerful drill would have proved to be a moderate or low hazard. So, yeah.
Very nice talk. A lot of learnings from it. Two things. One is a clarification question. You show the gravity residual on the left-hand side and the other one on the right, and it has changed all of a sudden. Did you acquire new data or a new way of interpolation? And the second aspect of it is, when do you do 3D geology block models? Because it looks like boreholes are just used as indicators. You still rely only on geophysics and exclude the geology as the geology block model.
So we would normally not do, well, we would do 3D models in the sense that we would physically draw cross sections through that. That's certainly a step that's coming up on that one that I'm still busy with. And it is advocated as something that people should do. But it's not, quite often it's not. But it's yeah, that would be included as part of the analytical process in terms of assessing the overburden in particular. So that was your second question. Those two maps were both residual. The first one was produced on the strength of only 4 or 5 boreholes. The second one was a remodeling using another 15 or whatever boreholes that were that had been drilled subsequently. But what had happened was that those engineering geologists who had done those extra 15 boreholes had never gone back to the geophysicist and said, please, can you remodel? This is not making sense. Okay. I'm trying to get away.
Tony, something, I hope I'm not springing on this on you, but on the 4th of August, there was a notice in the Government Gazette and a proclamation in terms of the Disaster Management Act saying the classification of a provincial disaster in terms of Section 23 of the Disaster Management Act, a life safety impact of sinkholes in the Merifong City local municipality. What does that mean for us or for the engineers? Is that, what does this all mean? Do you...
I think it means that government intends to spend a lot of money on doing investigations, but I'm not familiar with the Merifong situation. That's the old Carltonville area, isn't it?
Yes.
Yeah. So I'm not actually sure. I'm not familiar with it. Ilse, I don't know if you have, or you're familiar with the Merifong. Yeah. Where Ilse is going to be talking shortly and she can, or Janette. Yeah.
We need 2 microphones, people.
Right, can I?
Hello. So what happened in Merifong is that we had an investigation. There's been loads of sinkholes over the years. So there was an investigation that actually classified certain areas in Merifong as very high risk to live. So they are moving those people out. They're busy, in HPRC is busy with new areas for RDP houses. So all those people are going in time, move to a new area.
Just DP, did you want to say something? Because that was linked.
The second that made sense.